We have a flask. There we go. Looks like this. Has a volume of 540 cubic centimeter. Contains in it, it's filled with gas. So the gas inside that, this is gas here, has a mass of 0.430 gram at pressure P of 145,000, that's K Pascal, so 145,000 Pascal, at temperature T of 330 Kelvin. And the question is, can you tell me what the molecule mass of the gas? The molecule mass of the gas. Now, if you don't know what that is, look at the units. It says gram per mole, which means take the mass and divide it by the number of moles. The units are telling you what you have to do. We know what the mass of the gas is. So M, the molecule mass, equals the mass divided by the number of moles. Gram per mole. Well, we know what the mass is, what? 0.430 gram. So if I know what the number of moles is, if I know what that answer, I'm done. How do we find the number of moles? Well, we have an equation that says what? P times V equals nRT. P is the pressure, 145,000. V is the volume, which is, this is in cubic centimeter, you're going to convert it to meter. Here we go. 540 centimeter cube. How do you convert that to meter cube? 1 meter has how many? 100 centimeters. But these are cube. You got to cube each one of them. Equals, and that's what we're looking for. R is what? Is it 8.31? It's a constant. Times the temperature, which is what? 330 Kelvin. So let's see what we have here. 145,000 times 540 divided by 100 cube, 78.3 equals 8.31 times 330. 2742.3 N. Can we get how many moles in that flask? 78.3 divided by that number is 0.0286. And once you have that number, come back with it and put it right there. So 0.43 divided by that number, and I came up with 15.06 gram per mole. And your numbers are 3 significant digits, so it's at 15.1. So it's 15.1 gram per mole. So the molecule mass, when I read that, I don't really know what that meant. I forgot my chemistry, it's been years. So I looked at the units as gram per mole. So if I know how many moles and I know the mass, divide them and I'm done. So I shifted my focus on finding the number of moles, and that's what I did here. And once I got that, I went back to it. I said, I have that many grams, I have that many moles, divide them, and that means 15.1 gram per mole. Number 20. Again, we have another flask, but it's a cylinder shape. You push down on it to decrease the volume. It says flask is fitted with a straight piston. There's a piston that goes up and down to change the volume. That's free to slide up and down as shown in the figure. A mass rests on the top of the piston. So we have a mass to push it down. It says, here's the good news. Ideal gas at constant temperature. Temperature is constant. At 313 degree Kelvin. Initially, the pressure applied to the piston is 140 kilopascal. P initial equals 140,000 Pascal. And when we have that, the height here, I'm looking at like a little portion of the screen, trying to read through a little portion, is 23.4 centimeters. When adding a mass to it, so you go and add more mass to it, and what happens, this arm moves down. And now the new height is 16 centimeters. Find the new pressure. Find P final. Now we can derive the equation, but we probably have them. When you have a constant temperature, it should say P1 V1 equals P2 V2 somewhere in our notes, right? Do we have that in the notes? We can derive it. But I think probably giving you that somewhere. And the reason I said, because you have PV equals nRT. If your temperature is constant, R is a constant, N is a constant, so this doesn't change. So that says initial temperature times the initial volume equals the final, not temperature, pressure. The final pressure times the final volume. Or P1 V1 equals P2 V2. That's how we wrote them. What's pressure 1? Initial pressure. 140,000. And what was volume 1? Well, look at that shape. It's a cylinder. So the volume is what? Area times height. Area times the height. What was the height? 23.4 or 0.234 meters. The cross-section area, which is pi r squared, times the height. What is the final one? Well, P2 times the volume. Well, that cross-section area never changed. Only the height went up and down. So the area stayed the same. But the height now is what? 0.16. And if you look at the math, pi r squared, which is the area, cancels that area. It's the same area. That never changed the entire time. So now we do the math. What is P2 equal to? 140,000 times 0.234 divided by 0.16 equals, now is what? 204,750. They want it in Pascal. Doesn't say kilopascal in Pascal. I'm seeing all the numbers to be 3 significant digits. That's what, 205? The volume decreased, the pressure better increase. 205,000. Correct. Notice the way I was looking for, the first volume was given to us in kilopascal. It says 140K. But they wanted this in Pascal, not in kilopascal. I was just curious. I kept looking at it. The first one in kilopascal, but they want the answer in Pascal. In Pascal, 205,000. If in kilopascal, that would be 205 kPascal. But they want it in Pascal, not a kilopascal. Just bizarre. They give you 1 kilopascal, but they ask for it in Pascal. $58. Okay, let's see what 58 is. Okay. We have a block of ice. We have no idea what the mass of it. Ice. The mass is unknown. It is at negative 10 degrees Celsius. Bless you. Heat was added to it. Q was added to it. How much Q was added to it? 8 times 10 to the third, or fifth. 10 to the fifth joules, 5. That's the Q added. And when we added that, it says all the ice melted and it turned to water, converted to water now at 15 degrees Celsius. So basically you took a block of ice, you took one of those blow dryers, and you held the blow dryer at it at high temperature for a while, adding that heat to it, and what's going to happen to that ice? It's going to melt and raise the temperature to 15 degrees Celsius. The question, how much ice did we have to start with? What was the mass of it? So obviously the ice is going to gain some heat. This is lost. That heat you added, actually, we lost it because it was temperature, high temperature. When it hits the ice takes it from it. So the amount of heat that was taken by the ice, first we had to melt the ice, or before that, actually, before we melted even, because what was the temperature of the ice? -10. You can't melt it till you go ice from -10 to 0 first. Then you're going to melt the ice, and now it's at still 0 degrees Celsius. It becomes water at 0. Then you're going to take that ice, or that water that's melted now, the melted ice, which is water, and from 0 degrees Celsius to what? To 15 degrees Celsius. And when you take all these numbers and add them, that's how much heat was required. That's the 8.0 times 10 to the 5th. That's the result of all the heat we added. Let's see. Ice. I think ice is going to be the mass of the ice, C of the ice, times delta T. Melted, M times L. L for fusion. Plus, this will be M of the melted ice, which is water, C of the water, times delta T. The mass of the ice, unknown. C, I think, is 2090 for ice. I think it's 2090. Let's double check it. Where'd you go? Specific heat for ice. I'm almost positive it's 2090. Ice, 2090, yep. Final temperature, which is 0 minus the initial minus a minus 10 plus 10. The mass of the ice unknown times, we're going to add heat to melted. That's 33.5 times 10 to the 4th. This becomes water, mass of the water. C is 4,186. Final temperature 15 minus the initial, which is 0. All that should equal 8.0 times 10 to the 5th. So let's do the math. $20900M plus 33.5 times 10 to the 4M plus 4186 times 15, 62,790M. All of that equals 8.0 times 10 to the 5. Let's add them. I came up with, if I did my math correctly here, 418,690 M equals 8.0 times 10 to the 5, and the mass will be 1 1.91 kilogram. Two significant digit, 1.9 kilogram. Nope, 1.9, not 109. So that's what the mass of that ice. First, we have to take the ice from -10 to 0. We're going to melt it. We're going to becomes water from 0 to 15 degrees Celsius. And the last one, okay. We did this same example 2 minutes ago. You have 4 kilogram of copper at -15 added to, so you get a cup that's aluminum. The mass of that is 74 grams at 4 degrees Celsius. Has water in it. Mass of the water is, in that cup, is 120 grams at 4 degrees Celsius. And you take now a copper bowl and you drop it in. The mass of the copper that you dropped in is 45 grams or 43 grams, whatever it was. Can't see it. At -15. Find the found temperature. And look at the second question, which says, what mass of ice, if any, is present? How much ice is present? So the fact they're asking for that question, what percent, or what is the mass of the ice that's present? So maybe I should make an assumption some of the ice will freeze. Notice the water is almost freezing temperature. So you're adding something very cold. There's a good chance maybe some of that water will freeze. So that's, I'm going to assume some, not all, some of the water will freeze. That means if some will freeze, final temperature is going to be 0 degrees Celsius. Who's going to gain is the copper. It's the mass of the copper, C of the copper, times the change in temperature. Who's going to lose? Well, the aluminum is going to get 0 degrees, going to lose some heat. Mass of the aluminum, C of the aluminum, change in temperature, plus the water, mass of the water, C of the water, times change in temperature, plus part of the water is going to freeze, M times L. Part of the water will freeze. To freeze, we have to use change of phase. That's where L comes in, the latent heat. Copper again. Specific heat for copper, 387. So the mass of the copper, I can leave them in grams, by the way, I'll be okay. Mathematically, I'll be okay. Final temperature minus the initial temperature. I'll make it 0.04. And the reason I'm making it point, because if somebody else looking at the video, I'm going to say, why didn't they convert that to kilograms? It's supposed to be, but mathematically it really doesn't matter. Final temperature, which is what? 0 minus the initial minus the minus, that's plus 15. The mass of the aluminum, 0.074. C for aluminum, 900. Final temperature, 0 minus 4. Mass of the water, 120.120. 4186. Final temperature, T minus the initial, which is 4. And now we're saying a portion of the water, we're not sure how much, we'll call it M, times L. Now, water is going to freeze, it's going to lose some heat, that's a minus 33.5 times 10 to the 4. All of that should be 0. All of it should be 0. So let's try some calculation. 0.043 times 387 times the 15. This number is 249.615. Point, not a comma, point. 0.074 times 900 times a negative 4. That should be a minus now, not a plus. $266.4. This is actually my mistake. That should have been a 0, right? Final temperature is a 0. So this number is going to be a negative 0.120 times 4186 times a negative 4, 2009.28 minus 33.5 times 10 to the 4 m equals 0. If we take all these numbers, add them, and move them to the right side, when you move them to the right side, they become plus. If I did the math correctly, that's equal to plus 1992.5, and this number is negative 33.5 times 10 to the 4 m. You divide by m, that's a negative value, which says something is not right. How can the mass be negative? So my first assumption says, what part of it? Maybe some of the ice will melt, will freeze. It says, no, that's not working out. The other option is all the ice will freeze, or none of the ice will freeze. So which way you want to go?
All the ice.
All the ice? Okay. So let's assume all the ice will freeze. That means final temperature is unknown. Just because it froze, it doesn't mean the temperature is 0. It might be minus 2 degrees. All the ice will freeze. T final is unknown. We don't know what that T final is. Could be -2, -3, -1, -4, -0.5, who knows? Q gain plus Q loss equals 0. Who gain heat? We take that copper, which is the mass of the copper, C of the copper times delta T. Who lost? Well, first going to be the water is going to go from 4 to 0. The aluminum too is going to go from 4 to maybe -2, -3, who knows? It's not going to change the phase for aluminum, but the water will. So mass of the water times C for water times change in temperature to go from -4 to 0. Then you're going to freeze the water, all of it. Then that frozen water becomes ice, mass of the ice, times C of the ice, times delta T. All of that should equal to 0. Again, mass of the copper, 0.043 times 387. Final temperature minus the initial. We're not sure what the final temperature is. Mass of aluminum, 0.074. C for aluminum, 900. Final temperature minus the initial, which is what? Was 4 the initial? This is water to go from -4 to 0. Zero minus 4 degrees. Now we're going to freeze the water, all of it, 0.12 times -33.5 times 10 to the 4th. And once you freeze the water, it becomes ice. The mass of the ice, 0.12, that doesn't change. C for ice, 2090. Final temperature minus the initial temperature. So the water is going to go from -10 to 0. Freeze the water at 0. Then ice from 0 to whatever the temperature is. There we go. 0.043 times 387. 16, I'm going to just use one decimal place. 16.6 T plus 249.6 66.6 T minus 266.4. This will be a minus 0.12 times 4186 times the 4, 2009.3 plus, or that should be a minus, because then the second number is negative. 0.12 times 33.5 e to the 4, 4200 plus 250.8 T. Take all the ones with T, put them together and add them. I see one here, I see one here, and I see one here. And that'll give me 334 T. equals, take all the numbers, add them and move them to the other side. When I move to the other side, it becomes what? Uh-oh. Double check the numbers. I could be wrong. And I guess it's 126 degrees, which we know that's not true. Double check the numbers just to make sure. That can't be, because if it is, no water will freeze. So guess what? Maybe actually no water is freezing. So that can't be. So what's the only option left? None of the ice will freeze. As I said to you before, you could be there spending a long time. None of the ice. Assume none of the ice will freeze. Final temperature is T. Well, here we go. Let's see. Q gained, Q lost equals 0. What's gained? The copper. Lost is the water. And the aluminum. No freezing, nothing. No changing phases here. T minus a minus 15 plus 15. Mass of the water. What was the water? 120? 4186. T minus 4. Mass of the aluminum, 74. Times C for aluminum, 387, right? Was it 387? Oh, aluminum is 900, I'm sorry, 900. And final temperature, T minus 4. Hopefully this will do it. That's the only option. So if this doesn't work out, that means I multiplied somewhere wrong. 16.6 T plus 249.6 plus let's see what 0.12 times 4186. I got 502.3 T minus 2009.3 0.074 times 900 66.6 T 266.4 equals 0. Take all the ones with T, put them together. 16.6 plus 502.3 plus 66.6, 585.5 T equals, let's add all the numbers, move them to the right side. 249.6 minus 2009.3 minus 266.4. Perfect. Move them to the right side, becomes a plus 2026.1. What's the final temperature? .5 degrees. So we were right. None of the ice will freeze, and the temperature is 3.5. But it's misleading when you look at it, because it says what portion of the ice froze. And you think something froze, but when you do the math, it says, oh, nothing. What mass of the ice is present? How about 0? Yep, that was it. No ice there.